In this video, I will show you how to make a bipolar PWM in Simulink for a full-bridge inverter. So this is what it looks like. So I will make it from scratch. So let's make a new document here. So first we can add the switches. So I will add some IGBTs with diodes. So we can just run them in both directions. Then I just copy those. So we have 4 of them. And then I connect them. And then we need a input voltage, which is a DC voltage. So we use a DC voltage source. And then we can just connect them, all of them. So this is basically in the inverter. So I want to add an input voltage. So I've just predefined an input voltage, which is 400. And then we also need the gate signals. So I'll just use some from ports for this. I will call this one S1. Then I will copy that. And then we need to invert the signal. So I will add a NOT to invert the signal. And then we can just copy this because we want to do the exact same thing for the other side here. So we'll just move it a little bit to the left. But here we want a different gate signal. We want S2. And then we want a way to measure the voltage that comes out. So we will add a voltage measurement. So maybe I will just move this one a bit up. And then we have a voltage that we generate. So it's the voltage between the legs that we want. That is the output voltage. So now we want to make the gate signals. So that we would do with, I have a document here where I explain everything. So if you want that, it is in the description. Yeah, so here is the bipolar block diagram. So this is the equation for the duty cycle first. So we will make that first. And then we will generate the PWM afterwards. So we first need a reference voltage and then the input voltage. So because the input voltage is constant, I will just add a constant block. But ideally you want to measure it. So we'll just add Vn. And now we want the reference voltage to be sinusoidal. So we can add a sine block. Because this is an inverter. So we want an amplitude of the square root of 2 multiplied with Vref. So Vref is just a variable that I've predefined. And then we want the frequency of 50 Hertz. So I also define that. So here it's in radians per second. So we need to multiply with 2 times pi. So that is for the reference signal. So here we have the reference signal, and then here we have the input voltage. So we wanted to divide by 2 times the input voltage. So then we add a divide. And then we need a gain for this one. And then we insert that. So this should be 1 divided by 2. And now we need to add 0.5. So we have 0.5. No, first we need a constant. And then a sum. So we want to add, so we just change the arrangement there. So now we have the duty cycle. And then we need the PWM. So I will just add a comparator. So it's called a relational operator here. Then we'll just change the sign. And then we need a carrier. So it's called a repeating sequence, I think. repeating sequence. Now we want to make a triangular waveform. So at time after half a switching cycle, I predefined some switching frequencies here, and then another time at one switching period. So at time 0, it should be 0. At time after half a switching cycle, it should be 1. And then 0 after one switching cycle. So that gives a triangular waveform. And then we have the gate signal. So if you're not familiar with how this works, go ahead and watch my other video and where I explain the PWM mathematically. So the bipolar PWM mathematically. So this should be the bipolar PWM. So now we need to add some scopes. So add one there, and then we can also look at the duty cycle, and we can also take in the PWM as well. I will just make this one larger. Then we can add the PWM, and then we can also add, we can just add one of the duty cycles. We don't need both. So let's run this for one cycle, because we determined this to be 50 Hertz, this FAC. So that's one cycle of the reference frequency, reference voltage. And then we also need a power GUI. And because we have a PWM, which switches very fast, we need a discrete time sampling. So I think 1 microsecond is perfect for this. Even though it's a bit overkill. So you can see here that we get, this does not seem right. Now let's look at the duty cycle first. So you can see that the duty cycle is too large. Let us see what we did wrong. Yes, now I see it. We need to multiply with 2, not divide by 2. So it's multiply with 2 here. That is why we got a too large duty cycle. So it goes into overmodulation. So that means that doesn't work. So now, if we try it again, now it works. So you can see that on average, this seems to be sinusoidal, right? And you can see that the duty cycle is between 1 and 0, which it must be. And then we have the gate signal in orange here. Now, this is maybe not very interesting. So what we can do is that we can add an LC filter. So we can add a branch here. So if we just make this one an inductor, yeah, that is a nice one. That is a nice value. And then we need a capacitor here to get an LC filter. We need to increase this, let's say 100 micro. And then we add this to the output voltage. And now for this LC filter to work, we need a load. So we just add a resistive load of R, and let's set that to 10 ohms. And now we need to add another measurement of the average voltage. Now this is just a poorly designed LC filter. It will probably not work very well, but let's see how it works. So yeah, you can see that on average, it is a sinusoidal signal. So if you improve this filter, you will get a better sinusoidal waveform. So that is basically how a bipolar PWM works and how you can model it in Simulink. Now, if you want this PDF that I just showed you, you can go into the link in the description. And I will also make YouTube videos on every single topic in this mini course. So here we have the PWM that I'm working on now. And then next video will be about the unipolar PWM. And then also another type of a unipolar PWM. And in this document, I also explain how a full-bridge inverter works and also how PWM works, so you don't need a lot of background knowledge for this, just math and basic electronics.